Hello and welcome everybody. Today in calculus, we will look at the techniques of integration as a whole. So meaning if you're just given an equation or actually an expression that you want to take the antiderivative of, how do you figure out what strategy or which technique to use so then that way you can solve for it, because there are technically 5 different techniques that we learn. And yeah, we just need to know or be able to identify which one is which situation then. So let's go ahead and jump straight into it. And we're going to go through each technique and then look at some of the possible integrations that we can do according to the form. So when it comes to techniques, let's just kind of go in sequence. The first one that we learned is the use substitution. Now that's the most basic one. And keep in mind that when you're going through this entire list, when you look at any problem, you always want to go in the order of the way that we learned it, meaning always try to do use substitution first if possible, and then afterwards look at integration by parts and then by trig substitution and so forth and so forth and so forth. Okay, that's assuming that you don't know what to do for which techniques. Okay, so here for the use substitution, if you remember correctly, the way to look for if you're going to use a use substitution or not is look at the expression, and if you notice that both u and du is in the integral, then that means that you want to use a use substitution. So here are a few examples where use substitution would be viable. Notice that in my first case over here, you can see that du is going to be sine of x dx if you let u equal to 1 plus cosine of x. So normally what I like to do is just write out for both of them just to see if it actually makes a perfect fit. So u is going to be my inner function, and you can make this one more complex if you like. So this is going to be the reason why we include that 1 in there. Okay, so then that way when you solve for du, you can see that present inside the expression then. So du is equal to sine of x dx, and that works out nicely. Note that you should always write the dx part, which a lot of people don't, but you really should, just so then that way you can see what gets replaced. And in addition, the du expression should always be in the numerator, never in the denominator. So if you have a rational expression, u is most likely the denominator part, whereas du is going to be the numerator part. So that is going to be the first one. Now for the second one over here, sometimes in this example, you'll notice that it doesn't really look like there's a u and there's a du. And what I'm trying to say is that sometimes you might have to do a little bit of algebra to be able to see the trick. Now, if you look a little bit carefully, you'll notice that the bottom part, we have 1 plus 9 to the x. Well, if I rewrite that as if I rewrite that as 1 plus 3 to the x quantity squared, and then you have the dx and the 3 to the x over there, then you can probably see what your u substitution is going to be. Letting u equal to 3 to the x, and then so du would then be equal to 3 to the x ln of 3 multiplied by dx. So in this case, then you're going to get some sort of tan inverse with 3 to the x in there. And as much as I would like to include the 1, unfortunately I cannot, because remember, u has to be something, it has to be some sort of inner function. So I cannot include the outer part of it. Now for this last one over here, again, this is more like an algebra trick in order to be able to see what this is going to be. We have 1 plus the square root of x raised to the 8th power. Now, first of all, some people might say, okay, well, why don't I take the whole thing and expand it out? But then, that's not exactly going to be easy, because you have 9 terms that you're going to have to expand out because it's to the 8th power. So something that comes to mind is, okay, well, what if I do a u substitution? In my u substitution in this case, I can go ahead and say that let u equal to 1 plus square root of x. But now if you notice that du is not quite there, because that's going to be 1 over 2 root x dx, and there is no denominator in this case. But it's not to say that this is a bad example or a bad idea, because we just have to kind of work around it a little bit. So here, rather than making it this way, here's what's one thing that you can do with a u substitution that's a little bit tricky to help you out. Go ahead and let u equal to the square root of x in this case. Now, again, if you want to include the 1, you can go ahead and do that. And before you take the derivative, here's what I'm noticing. I can go ahead and square both sides, and so we get u squared is equal to x. Now, if you do so, then that means that 2u du is equal to dx then. So now notice then we can go ahead and plug it back in, and you're going to get everything that is in terms of u. So that now becomes the integral. The dx part, that is going to become 2u du. And then the inside, inside there, that will now give us 1 plus u quantity raised to the 8th power. And that's something that we can actually deal with in this case then. Now, this is where I'm thinking to myself, okay, maybe I should have let u equal to 1 plus the square root of x then. It's still going to have the same effect, and you can probably solve for this way, and that might be a little bit easier to deal with. Okay, but those are the examples of u substitution. Okay, the next type of integration that we look at is something called integration by parts over here. Okay, so for integration by parts, what you're looking for is the following. You're going to use integration by part if you see a product or a ratio where the two factors have no relationship. So meaning that, you know, if you look at two parts of the equation, whereas u substitution, you can see one is the derivative of the other. In this case, they have no relationship. Now, in order to use integration by part, you got to remember to make sure the following has to work. Make sure that one of the factors you can easily take the derivative of, while the other factor you're going to have to integrate then. Okay, because remember, you're setting one as u, the other one is going to be dv. And the final thing is that if you have to use integration by parts more than 2 times, then there is a trick to it, or you might have just done it wrong. So it could be one of those cases. So here are some examples of integration by parts then. So in this first example over here, you'll notice that, yes, you do have a product, right, of two functions, and they have no relationship to each other. So that means that we can go ahead and use integration by parts. In terms of which one is going to be which, one is going to be equal to u, the other one is going to be dv. Now, remember, u you're going to take the derivative of, whereas dv you're going to take the antiderivative of. So I usually use u as the one that we can always diminish. So in this case, it's going to be the polynomial function, whereas dv is going to be equal to e to the x dx, because that one I can easily integrate then. Okay, so always try to use u as something that will diminish if possible. Okay, so then now you just go through the procedure and say du is equal to 2x dx, and then v is going to be e to the x, and then, you know, go through the motion of solving for the rest of it. Now here in the second example of integration by part over here, it doesn't look like it's much in terms of like, you know, working with stuff that you can work with, but you actually still have a u and you still have a dv. In this case, u is restricted to just strictly cosine of inverse of x, because that's the only function. Now the dv part right here, if you don't see it, well, that could be just strictly equal to dx. Right? You know, we never really kind of see it that way, but it's actually possible to use. So now we can go ahead and say du is equal to 1 over the square root of 1 minus x squared with a negative on the outside, whereas v, well, that's just going to be equal to x. And once again, if you use u dv minus v du, then you're going to get another part, which I do believe that it comes out to be you do a u substitution to do the second integration then. Okay, so there it is. That's for the other one. Now for the last one, again, this one is going to be more of an algebra trick, because you'll notice that I did say a product or a ratio, right? If you look at the top part over here, a product or a ratio. So here in this third example, you have a ratio. Now, if you're wondering, well, okay, well, how do you work this out if it's a ratio? Well, you can just probably rewrite it then, okay? You'll notice that this right here, I can write that as x multiplied by cosecant squared of x dx. So then now we can see which one is going to be which one. So u is going to be equal to x. So du is going to be equal to dx. But whereas dv is going to be equal to cosecant squared of x dx. So therefore v is going to be equal to negative cotangent of x then. Okay. In the case of where you have to do it more than 2 times, in the case of where you have to do it more than 2 times and then it becomes something funky, is if you have something like, say, e to the x multiplied by sine of x dx, and you're trying to integrate that. The problem is that when you try to use integration by parts, you'll notice that it repeats back to the very beginning. And so that means you have to subtract or add something to the other side and then divide through. So if you want, you probably want to take a look at the video that I made last time so you can see how that example actually works out then. Okay, but for the most part, integration by parts, you should not have to use more than twice, unless, either A, you did something wrong, or B, there's a trick to it, or C, the author just wanted to pull something, pull your leg or something like that. Okay. All right. So that's technique number 2. So technique number 3 for integration is called trig integration. So this one is when you see a trig function or trig functions raised to some power. So for example, over here, you can see my 3 examples. They all involve some sort of trig function with some sort of exponents. So the idea here, or the strategy here, is to diminish one of the exponents. So then that way, maybe you can use like a u substitution. So in this case over here, what we can do is we can first make a trig substitution for sine. So here we're going to go ahead and write that sine cube as sine squared multiplied by sine of x dx. Because if you remember, cosine and sine, they're related to each other by the derivative. So this part right here, I like the sine part because I'm going to keep that part as my du. I'm going to keep my sine dx as my du over here. So that tells me that u is most likely going to be equal to cosine of x. Now, the question is then, what do you do with this sine squared? Well, you change that into a cosine then. So then that is now going to become 1 minus the cosine squared of x. And then we have sine of x dx. So this integral now becomes cosine to the 7th power of 1 minus cosine squared of x, and then we have sine of x dx. So now we can see let u equal to cosine of x, so du is equal to the negative sine of x dx, and this now becomes an easy integration by using a u substitution. So integral of u to the 7th, and then we have 1 minus u squared, and then this is going to be negative du, and you can probably take it from there then. Okay. For the second example, it's kind of the same idea. We have tangent raised to the 5th power, and you have to think to yourself, okay, well, tangent's derivative is going to be secant squared. So you need to somehow extract that out of the equation then, or the expression then. So what I'll do is I'll just do exactly the same thing. We'll take a piece of tangent and then somehow get a secant out of it. And the best way to do that is to take out a tangent squared. So this tangent x cubed, tangent cube x, then we also have the part that I'm going to change, which is going to be the tangent squared x dx. So take this guy right here, change it. So we have tangent cube x, and then we have tangent squared. That is now the same thing as secant squared of x minus 1 dx. Then we can go further by saying, okay, let's go ahead and multiply everything out. So tangent cube x times the secant squared, and then we have dx. And then we also have the other part over here, because when we multiply out, you'll notice that there's another tangent cube. So that means that this is going to be there then. Now, the first part we can integrate because we can see the u, and then we can see the dv part. So u and then this dv. But this second part over here, where we have the tangent cube x, we're going to have to repeat the process one more time. So what that means is we're going to have to take that guy, right, and break it exactly the same way as how we broke it the first time around. So take out the tangent of x, and then take out the tangent squared x, and change that into a, once again, secant squared of x minus 1 dx. So you can see how each time we are diminishing the power. So then that way, if I can find it one more time, okay, there it is. So each time we are diminishing the tangent exponent, so then that way we can introduce the secant squared. So then eventually we can get to the antiderivative then. Okay. The final way of trig integration is this guy over here, which is secant to the 4th power, where you don't have any cosine. So in this case, the exponent is even, and the trick to this is we have to use a double angle substitution in order to make this work. So the substitution here is that we say that secant squared of x, that is going to be equal to 1 minus cosine 2x, and then all divided by 2 then. So in this case, we have 1 minus cosine 2x divided by 2 quantity squared. And we're going to have to expand that guy all out, which will give us 1 minus 2 cosine 2x and then plus cosine squared of 2x all divided by 4. Keep going. We don't like this the last part. Actually, we don't like that last part. So we're going to have to take that cosine squared and change that also using a double angle formula. So if you remember correctly, cosine squared of u is equal to 1 plus the cosine 2u over u. So this now can become one of the following then, which is 1 plus cosine of 4x divided by 2. So then, you go through the motion of solving for the antiderivative then. So the idea here, again, is just to diminish your exponent as much as possible to the point where you can actually take the antiderivative. And that's trig integration for you, okay? Okay, after that, you learn the next one, which is called trig substitution. So that means that if you are going to have something where it's like a polynomial, usually something that's quadratic, you can replace it by saying let x equal to sine or let x equals to tangent or something. So the way or the thing that you're looking for is any time that you see the following form, especially in the denominator, this is where you use the trig substitution. So we have, if you have like say a difference or a sum of squares, where it's like x squared plus or minus a squared, or maybe the reverse of that. If you have like a squared minus or plus, in this case, x squared. So either one of those are okay. If you have a variation where what we have above is going to be inside the square root, that should be okay too. And the last one is if you have a quadratic that can be completed the square to get some sort of sum difference of square then, okay? So here are three examples of where you use a trig substitution. So if you look at the bottom part right here, you have a quadratic, and sometimes when you look at it and you see a quadratic, you always think to yourself, okay, well, is it factorable or is it going to be complete the square part? Well, this part right here is going to fall into the third category where you have a quadratic and you can use a complete the square. Because if you look at the denominator, you'll notice that that is going to be, that can be written as the following. The square root of x squared plus 10x plus 25 plus 1. And when you write it like that, then you can see that the bottom part will now give you x plus 5 quantity squared plus 1, and then we're going to have the square root of it. So at this point, we go ahead and say, let u, I'm sorry, not u in this case, because we're using a trig substitution. So we're going to go ahead and do that technique where we say let x plus 5 is equal to what squared plus 1 is going to give us something nice, and I think that's tangent. So x plus 5 is going to be equal to tangent of theta. And then you take the derivative, make a substitution, and draw the triangle and all that other stuff then. Okay, so that would be an example of where you have the quadratic. In the second example over here, you'll notice that, yeah, we do actually have a quadratic, but unfortunately, we don't have like x squared minus we don't have a difference of square. We have a difference of, well, quadratic in this case. And that's okay. We can still work with that because that 5 right there, we can look at it as x squared minus the square root of 5 quantity squared. And then in that case, that you do have a difference of square in this then. So in this scenario, we can go ahead and do exactly the same thing. We can go ahead and say let x equal to, in this case, I need to deal with the 5 or compensate with the 5. So that means it's going to be equal to root 5 multiplied by, let's see, what squared minus a constant is going to give you something nice. So I think this is where we're going to use, I think, secant, if I remember correctly. So it's going to be secant of theta. And then just like the first one, then you're going to go ahead and solve for dx. And then that's going to be in terms of theta, and so on and so on and so on. Okay, so don't let that x squared minus 5 hinder you. You can still use a trig substitution in this case. And finally, for this last one over here, you can see that you have in the denominator the square root of difference of square. So then we can go ahead and do exactly the same thing. So we're going to go ahead and try to make a substitution then. So in this case, I'm probably going to take the whole bottom part right here and maybe rewrite it so you can see what the substitution is going to be then. So we have 3 squared minus 5x quantity squared then, okay? So in this case, I'm going to go ahead and like make a replacement for 5x over there. 5x is going to be equal to, let's see, a constant minus a trig function is equal to something else. So maybe I can use sine in this case, right? So sine of theta. And remember, you have to compensate for that 3 squared. So that means that it's going to be 3 sine theta. So once again, we make that substitution and then afterward draw the triangle to see how this all works out. And again, if all of these techniques look somewhat familiar, but you can't figure out like how to actually continue and solve for it, go back to those videos and take a look at how you're supposed to do these then, okay? All right. The fourth technique over here, actually the fifth technique, because I just kind of sneaked down, take a look, and it's the final thought, is called partial fractions. And for partial fraction is actually very distinct, just like all of them. So again, you're going to look at your expression, and if your expression is a rational function where the denominator is factorable or can be divided through, then that means that's where you're going to use a partial fraction. So for example, in the first case over here, you'll notice that the bottom part, this thing definitely can be factored. So that means you have x squared minus 1, and then the bottom part we factor out an x, and what's left is you have x squared plus x plus 1 dx. So if you remember correctly, the way it works is we're going to go ahead and say x squared minus 1 divided by x times x squared plus x dx, x plus 1 is equal to, the first part is going to be some constant divided by the first factor, and then plus the second part is going to be some constant over the second factor. But in the case of where the factor is something that is higher than the first degree, then that means that the top has to be 1 less than that then. So that means that this has to be a bx plus c, okay? All right, so my pen looks like it's dying, so I hopefully can finish this soon. And then that's where you're now going to solve for a, b, and c using some sort of combination of system of equation. In order to solve for this then, okay? Now, in the second example over here, there are times where your rational expression is going to be a case where the numerator is bigger than the denominator. And you'll notice the bottom part does not factor through, unfortunately. So that doesn't necessarily mean you can't do it, but that means you have to do a long division. So you're going to have to take your x squared plus 0x plus 9 and then divide through then with the other part. So we have x to the 4th plus 0x cubed plus 9x squared and then plus x plus 2. So you do your long division to figure out what this is equal to. And whatever your answer is something that is going to be a polynomial and then plus some sort of residual which you can hopefully integrate then. So just to kind of give you like a head start right here, then that means, let's see, the first part is going to be x squared because x squared times x squared gives you x to the 4th. So x to the 4th plus 0x cubed and then plus 9x squared over here. All of that cancels out. So it looks like all of that is gone. So all you have left is just the x plus 2 then. So then that means that this expression is now going to be x squared plus x plus 2 divided by x squared plus 9. And it looks like maybe we can finish this just for, good measures. So x squared plus x over x squared plus 9 and then plus 2 divided by x squared plus 9. So your final answer is going to be, let's see, looks like it's going to be x to the 3rd, 1/3. And then we have plus, this looks like a u substitution right here. So then that means it's going to be ln, absolute value of x squared plus 9. And I do believe that there is a 1/2. And finally, for the last part, that is going to be 2 plus the tan inverse of x divided by 3, and then we're going to produce a 3. So that means that this is going to be a 6, and then plus c then. Okay, so when I did this, it looks like I did it pretty fast and just right on the spot, and that's something that just kind of takes practice over time. So the more you do these problems, the better you're going to get at it, and then the faster it's going to go for you too, I guess too. Okay. And here, finally, for the last example, this one right here is going to be another example of partial fractions. And the trick is, if you remember that if your exponent, or well, if you have an exponent, then that means that you have to have a number of fractions that's equal to those exponents then. So in this case, this 5 divided by x times x plus 2 squared times x squared plus 1, that is going to break into the following partial fractions. It's a divided by x plus b divided by x plus 2 plus c divided by x plus 2 quantity squared. And then finally for the last one, which is going to be plus dx plus e all divided by x squared plus 1, mainly because this right here is a factor that is a second degree. And yes, technically this one is a second degree too, but because the inside component is a linear, that's why it's just c and not cx plus e then, okay? So if it's factorable, then we just go ahead and keep it as a linear. All right, so here are some final thoughts about all of this before you dive into it, okay? The first one is that you might have to do a little bit of algebra before seeing the form to determine the techniques of integration. So if you notice the problems that I did, I sometimes have to do a little bit of algebra trig or maybe some trig identity to make it a little bit easier so you can see how it works out. So that is always going to be something that you want to think about. And finally, practice to be more familiar. So when it comes to practicing, again, just try doing problems on your own if you can, and maybe work together if you can also, because, hey, maybe you solve for it one way and your friend solve for another way. You guys compare notes, and then maybe one is faster than the other. You like his technique or her technique, and then, vice versa. So just see what's out there. So then that way you can kind of improve your skill sets in this case then, okay? All right, thank you so much for watching. I will see you guys next time, and have a good one. Take care. Bye-bye.